Physics predicts one ultimate temperature, called the Planck temperature. Beyond it, our current equations stop giving reliable answers. That temperature marks where spacetime and particles blur together. Wide black vacuum makes heat feel abstract and distant. Temperature measures how fast particles jiggle on average. It captures random motion of many particles, not one object's energy. We care because temperature governs chemistry, structure, and life. At microscopic scales, energy distributes among many quantum states. Higher temperature means more particles occupy higher energy levels. Thermal interactions shift populations, and systems approach equilibrium over time. Boltzmann's rule gives probabilities for these energy populations. Imagine a gas bottle at 200 Kelvin inside space. Atoms there collide gently, and reactions barely proceed. So temperature is average motion, predicting material behavior. Deepest cold in physics is absolute zero, 0 Kelvin exactly. At that point, particles hold minimal quantum motion, but not none. This limit matters because it sets a lower bound on energy. Cooling removes energy from systems, and entropy typically decreases. Practically, we can approach zero, but never actually reach it. Laser cooling and evaporative cooling reach billionths of Kelvin in labs. Those ultracold clouds reveal quantum effects like Bose-Einstein condensation. For example, sodium atoms cool to about 100 nanokelvin experimentally. At these scales, atoms behave coherently, similar to a single wave. Absolute zero remains an unattainable limit, yet it defines coldness. Some cosmic events reach mind-bending temperatures, briefly and intensely. Young supernovae and fusion cores hit millions of Kelvin internally. The Sun's core sits near 15 million Kelvin, powering fusion continually. Supernova explosions spike temperatures to billions of Kelvin for moments. Human experiments also create extreme heat in tiny volumes. Particle colliders slam heavy ions together at near-light speeds. Those collisions form microplasmas hotter than stars for femtoseconds. RHIC and LHC experiments reach temperatures of trillions of Kelvin briefly. We study these extremes to learn about the universe's earliest moments. Measurement requires fast detectors and clever data reconstruction techniques. So real universe highs range from millions to trillions of Kelvin. There exists a theoretical ceiling called the Planck temperature. Its scale is about 10 to the power of 32 Kelvin. This matters because beyond that scale our concepts lose meaning. Gravity and quantum effects converge there, making standard physics inconsistent. Distances approach the Planck length, unimaginably tiny and fluctuating wildly. Particles blur into spacetime foam, and separate identities vanish. Simple estimates set thermal energy per particle near Planck energy. Numerically, that corresponds to about 10 to the 8 joules per particle. No experiment reaches these energies, so this remains theoretical today. The Planck temperature marks a boundary where known physics fails. Net result, it is the highest meaningful temperature in current theory. Why can't temperatures exceed the Planck limit in theory? Because energy densities would curve spacetime extremely and unpredictably. Curvature reaches scales where quantum gravity must govern behavior. We currently lack a complete quantum gravity framework to describe those regimes. Thermal fluctuations could create black hole-like regions locally. Those regions erase the separation between heat and spacetime geometry. Particle wavelengths shrink, and thermodynamics ceases to apply reliably. Thought experiments show measurement apparatus would fail under such conditions. Researchers hope a quantum gravity theory will clarify possible outcomes. Until then, temperatures above the Planck value remain undefined by physics. Bottom line, our equations stop giving sensible predictions at that boundary. There is a surprising concept called negative absolute temperature. It applies to systems with an upper bound on energy states. We care because such systems can appear hotter than any positive temperature. Population inversion traps particles in high energy levels, reversing statistics. Mathematically, the temperature variable flips sign since entropy decreases with energy. That negative sign means adding energy reduces entropy, counterintuitive but true. Experimental spin systems and cold atom traps demonstrate negative temperatures briefly. These states are isolated, and they relax back to positive temperatures quickly. Importantly, negative temperatures are not colder than absolute zero, they are hotter. In thermal ordering, negative temperatures sit above infinite temperature on the scale. So negative temperatures expand our idea of what hot and cold mean. Humans recreate extremes intentionally for research and practical goals. On the cold side, optical lattices and dilution fridges reach microkelvin scales. These platforms enable quantum computing and precision measurement breakthroughs. On the hot side, tokamaks and colliders create extreme microplasmas briefly. Tokamak plasmas heat to over 100 million Kelvin to fuse hydrogen. Colliders produce trillions of Kelvin in tiny volumes during particle collisions. Scientists use intense fields, compression, and relativistic collisions to inject energy. These conditions let us probe physics from the universe's earliest seconds. Detectors face huge challenges, surviving brief flashes of particles and radiation. Data analysis must extract signals from noisy and transient backgrounds. Net result, humans can approach cosmic extremes, but only fleetingly. Remember, the Planck temperature marks the ultimate theoretical temperature ceiling. If you liked this dive, subscribe for more curious physics explorations.